All right. Welcome back, Cohort 5. We are in our second discussion on Chapter 9. So, Andrew or anyone else who wants to write a question or raise their hand, let's just jump into it. Okay, I just heard the recording in progress thing. Maybe there's something about Pete's coffee that causes a time dilation. But either way, now we're in Chapter 9. So, where shall we begin?
Yeah, I was going to say if anyone has any particular points they want to get into with this chapter, happy to jump into those. Otherwise, if anyone's like, only able to make this meeting, weren't able to make the last one, I'm happy to kind of give a general overview of what's going on here.
If you don't mind, a general overview would be good to start with. If others are okay, means.
Yeah, go for it.
Previous meeting is at 11 o'clock at night in my time, so I haven't been able to make them. So general overview would be really helpful for me if it's a possibility.
Yeah, great. Yeah, let's do that. And there is a lot going on in this, this chapter. This is sort of aside from chapter 6, which gives us a general recipe for composing generative models and kind of the more general method you might take here in actually applying active inference in the second half of the book. Recall in chapter 7, we're given the POMDP model, how to construct that. Chapter 8, we're given more continuous models. And then here we bring it back to, okay, so how do we actually use these models and construct them in a way that we can apply them to empirical experiments where we're actually collecting real data. And so we're moving beyond the range of just purely building models and running simulations to collecting empirical data such as like neurophysiological data. It could be EEG, it could be just observing behavior of anywhere from human beings to rats, or if you're in more of an engineering setting, you might be looking at other kinds of data that's being extracted. And you just basically, we want to figure out how is that, what's the process that is generating that data, which of course we may never know, but we can attempt to model it. So yeah, this chapter, it's quite dense, I'll be honest, whenever we incorporate everything, but it does give us a nice full flow of how to apply these methods to empirical data. So first of all, in the introduction, there's hints at what we'll find in the rest of the chapter. We're introduced to meta-Bayesian analysis, which is where we actually view this as the agent's subjective model versus our own objective model that we're building of the agent's subjective model. That kind of carries into the active inference ontology, right? We do have to account for the fact that we are sort of the quote unquote objective scientists in this situation. We're attempting to model the behavior and other parameters of like a separate being from ourselves. Like in a T-maze, we're trying to, understand the subjective model of a rat, which we don't have it. Collecting data and applying analysis to see if we can do something like approximate it. So here our goal is to, what we would say is recover or infer the unknown parameters of, they phrase it as the subject's brain, its subjective model, using our own objective, just by drawing on the behavior in our observed data, and then we invert our objective model to infer those parameters of the subjective model. And then finally, by doing so, we can test and compare hypotheses. For example, we might find multiple models that we could build. We could compare them and see which one holds best to like the behavioral outcomes that we're seeing in the data. And then they have another concept called computational phenotyping. This is where we kind of, by recovering model parameters, prior beliefs of our agent, we could actually like kind of classify the individuals we're studying, whether it be multiple rats in a T-maze, it could be clinical patients and more of a, you know, in the study of psychiatry, but we can kind of phenotype those individuals based on what model we end up developing to try and explain their behavior. And so, yeah, this chapter lends itself really well to specifically computational psychiatry and neuropsychology and neurology, but in principle, all of these methods could be applied to a much broader variety of phenomena, whether it be or even non-living systems. So section 9.2, and again, there's a lot going on in this chapter, so I'm going to try to be a little bit more brief, but we are introduced to, just as we've seen Bayes' theorem in previous chapters, now we have equation 9.1, which looks almost exactly equivalent, other than we've replaced observations and states with behavioral outcomes, U, which are actions to be taken, and then a theta symbol, which represents the parameters of the model. And so just as we can update a model's beliefs related to states, observations, the relationship between them in the form of likelihoods and posteriors, we're ideally doing that same exact thing here, but now we're mapping outcomes to model parameters. And I'm going to pause here real quick. Prakash, you had a question?
Yes, actually, I'm just wondering. So you mentioned this computational, yeah, exactly this one. You mentioned computational phenomenology and this subjective model. Are you saying that I don't know anything about it, so I'm just asking. Are you saying that somebody can actually start plugging in values inside that matrix that you said, like, and there will be like what I'm saying is that the values which you encode into that and some variables since you encode will it be part of that computational phenomenology, or how does it go?
Yeah, sure. So one thing we could do to try and answer that question is to look at, like, we have in section 9.5 just a nice like brief series of steps for how to go about this. And so like in step 1, quite simple, we collect behavioral data. You could even think of this as like a spreadsheet or something along those lines, like that kind of structure where each row can represent an individual. Like in a T-maze example, we have rat number 1, rat number 2. We could have in the columns things like what are the actions or that they took that we saw whenever we collected the data. What are the associated observations or other components of a model that we saw. We could also have like other kinds of information, like maybe the test was being done by administering a drug to certain rats and not to others to try and study the impact, right? So we could have like a binary 1 or 0, like if for each rat, if it was administered the drug or not. Step 2, we formulate a POMDP. This chapter is a little bit heavier on looking at discrete models. So a POMDP, as we were introduced to in chapter 7, although later they do give us a couple examples of more continuous models. And what we're trying to do with step 2 is that we're trying to develop basically, derive a model that like closely approximates what we see in the data that we just collected in step 1. But nonetheless, we know that like this is our model. So this is kind of that outer objective model that we're seeing in the figure that Daniel's pulled up there, figure 9.1. So it's kind of that inner box is the subjective model. We're trying to basically, yeah, devise our own objective model of what's going on in the rat's mind, so to speak, if we follow Time's example. So that there could be aspects of this that, because your question had to do with specifying priors. Step 3 is specifying a likelihood function, and that's based on the model that we just tried to make. Then after that, step 4, we specify prior beliefs. And so in that step, the way they've written it, we can specify prior beliefs about the parameters in terms of expectations and precisions. Often these will be centered on 0 with precisions reflecting plausible ranges. So you might think of that as you have your own hypothesis about what the prior beliefs are. And you just kind of roll with it, so to speak. We're doing a process where we're trying to build a model that whenever we run that model, and run a simulation with it, hopefully it more or less approximates the real actions that, say, a rat and a T-maze took, as well as like the combination between those and the observations that the rat received. So hopefully that provided some kind of information or a bit of an answer to your question. But yeah, I'm just trying to get to the,
Yeah,
sorry.
that was a great answer. I'll add a little more. So Prakash, you mentioned phenomenology, like the kind of felt experience. And this kind of made me think about like 3 different kinds of phenotypes that you might be studying. You might be studying the most grossly morphological, like just the actual bodily movement, like the movement of an arm. Then there's kind of cognitive phenotypes that are internal, they're not directly observed, but they're also not like philosophical or metaphysical or phenomenological, like the motivational drive. Sorry, mainly I think I'll just type. I'll just type today, since it's a little strange with the internet. But suffice to say that the phenomenological phenotypes, like the felt experience, is probably the most difficult, because now you're not just talking about where the arm is in location. You're not just talking about the intent to move the arm or something like that, but you're talking about like the experience. And that is the challenge that many researchers are focused on.
And hey, Daniel, I want to give you a heads up that your audio is a little choppy as well, but I do find
I'm just gonna type. I'll just type.
Yeah, cool. Super helpful. Thanks. Great. And then yeah, I'll just follow through with those steps. Like after you specify those prior beliefs in step 4, step 5, we solve for posterior probability and model evidence. So effectively what we're doing is we're just kind of continuing the process of like, how do we approximate our subjects understudies subjective model. And so like here are all the different components, right? All the ones that we've been familiar with as we've proceeded through the textbooks. We're figuring out likelihood functions. We're figuring out prior beliefs, even if we're just setting them initially as like some value, and then need to kind of further carve out our model from there, and maybe update those priors to better reflect what's going on in the subjective model. So I think they repeatedly use this word recover, like we're trying to recover the prior beliefs or recover the parameters of the model. So there's no assumption that we know what these are from the onset. Instead, we're attempting to build a model and then kind of fine tune things from there to where they better approximate what might be the actual priors and the kind of likelihood and model evidence and so on that the agent is working with.
I'll just put one comment. So you're saying that if suppose we found some empirical study and we get the exact value, well, not exact value, but like a distribution, like a Gaussian distribution of the prior, then that will be the best. That will be very helpful, right?
Yeah, presumably. Yeah, if you find that.
So basically we are trying to iterate our model so that we can get to those kind of values which have a very accurate description of what the prior values exactly might be.
Yeah,
something on those lines, right? So some reverse engineering.
yeah, you're right. That's very right. Like we can just think of it as like we've been introduced to these sort of in silico synthetic models, like for example, a POMDP. We're already familiar at this point, thanks to chapter 7 and other chapters. Like, well, here are all of the components of a POMDP. We have our D vector, which is our priors over initial states. We have our A matrix of likelihoods. We have our B matrix of state transitions and so on. But now, whenever we've collected empirical data, well, we only have what we, as the so-called objective scientists, can observe. So we can observe, an agent's, like a rat's or a human being's actions that they've taken, and we can observe like maybe what was going on in the generative process. Like, okay, the rat was in a maze where the reward was on the left, right? So we have our knowns, but they're not and givens and what we observe, but they don't all match all of these different components of the POMDP. So we're attempting to kind of recover what's missing, right? We ourselves are undergoing the active inference process of trying to infer and learn what are the other components that we cannot directly observe of the rat's behavior. Because in that way, of course, it starts to match, anything else, some other machine learning routine or something. Like we're just trying to find these unknown parameters in what we presume to be the rat's model, subjective model.
Yeah, thank you.
Sure, absolutely. And then, aside from being either introduced or given some kind of more technical refresher on what methods we might use along the way to do this, like they dedicate an entire section to variational Laplace, which kind of gives more description on how we're using this modified Bayes' theorem. Now, instead of with states and observations, we have actions and we have like model parameters. Aside from how it reintroduces how we might recover parameters via the Laplace approximation, we also get a much more description utility of applying these methods in the first place, which is in step 6 of the overall process that's introduced here. And so it gets more into, there's a lot of overlap between this and other more traditional analytic settings where you might be trying to do something like a covariance analysis or correlation analysis. You might be trying to, as I mentioned earlier with a T-maze example where maybe a drug was administered to certain rats and not to others. Let's do some kind of group level analysis to see what are the patterns in the behavior and outcomes for the rats who were administered the drug versus those who were not. Right. So this is getting into much more, again, like kind of traditional settings where really you're just applying analysis. But now you have the added utility that you've devised an entire, like in this case, POMDP that can potentially like really strongly explain a rat's behavior. And you have all these different components and parameters that you've recovered to allow for a quite broad variety of analyses beyond just running like a simple like t-test or looking at correlation between certain behaviors and outcomes, and that's all we have. So that's the general process. I think that figure 9.2 does a rather good job of trying to visualize the 6-step process, collect data. We build our own our initial objective model of how we think that data is produced. We derive like a likelihood function. Step 4, prior beliefs. We set those. Step 5, we invert the model, which we're already familiar with doing previously in the book. I think that's how you go from a model, an agent who has priors and likelihoods, and then those can be mapped through Bayes' theorem to a posterior and model evidence. And so everything actually looks kind of structurally equivalent, right, to that equation. And finally, we move on to the final analysis. Yeah, Prakash.
Actually, I have a question. So what about if you are like, we don't exactly follow the likelihood function the way they're given, the way they're giving, but we introduce our own function which actually does the likelihood mapping, like not a function or a methodology, and on top of it, so actually fundamentally, like, we're using this Markovian processes to do the state transitions, right? So we have flexibility that we use. Uh, what I'm actually trying to say is that this likelihood function, right, which starts from the policy level, right, fundamentally down to the observation level, and instead of following the exact mechanism which they give, we can introduce our own methods, but we do the mapping of transitions across states, and the observation mapping, like the A matrix and the B matrix, we keep it very similar. But the other, the higher levels, that can plausibly be changed also, right? It's like we can apply free energy principle to that also.
Mm-hmm.
I'm just thinking on those lines. I've not been able to formalize it very cleanly, but I hope that in a few weeks' time I'll have more clarity. So that's what I was trying to understand. Fundamentally, we do this surprise minimization, the most core principle, and then the transition mapping. But the later above layers, like say policies and affordances, we can actually create a methodology which fundamentally does that, but not exactly through this very complex Bayesian mechanisms. That's just what I'm trying to say. It's like there can be other methods like to accomplish those policies and affordances.
Mm-hmm.
I'll see if if it will work. It's a very interesting question, and it makes me think that this is like a policy selection, but you're not actually choosing the policy, but it's trying to develop a function that does map from all of the model and parameters to the choice of policy. So it's kind of like policy selection from the outside, and then we have the view from the inside, view from the outside, and maybe there are some other heuristics or rules that could be simplifying in terms of how we do the policy inference.
Sorry, actually I couldn't hear. But you're saying policy inference will be from inside, right? Or you're saying it will be from outside? I don't understand.
Well, pi is usually how we think about policy selection from the inside, but we're the behavioral experimenter. We're only observing the emitted behaviors. So we're developing a model in step 3 that is the distribution of the emitted behavior given all of the parameters, many of which the subject doesn't have access to.
Daniel, just a quick heads up, your audio is still kind of choppy there. But I think you were making the point that, yeah, like whenever we've collected the data, we have access ourselves to what were the behavioral outcomes, i.e., whenever we're looking at equation, like the tilde u, that is a series of actions. The tilde always denotes like a sequence, and then u being an individual action. And so with the policy, you can think of a policy as a series of actions. Like the I don't know, we have like a rat in a T maze. Action 1, it takes a hint, as to where the reward is. Action 2, it goes to where the reward is as told by the hint. So now we have like a number of actions in a sequence, like at time step 1, it did this, time step 2, it did this. And that can be represented as the U tilde, which could also be represented as an individual policy. So a rat who really already thinks that the reward is on the left, it'll skip the hint, it'll go right to that reward, right? So we see we can associate a certain sequence of actions with this actual behavior that we see. It's equivalent. And then whenever we're looking at equation, it's like, okay, well, why did the rat jump right to the reward? Like, what parameters are in the model that would push it into that kind of behavior rather than the kind of safer policy of going for the hint first? And so that's what we're trying to kind of recover. Like, what are those parameters that are determining that? Given that we only know the actions that it took, we don't know all of these underlying parameters and cognitive parameters or otherwise. We don't necessarily know priors. We don't necessarily know how much the rat, like another thing that we get introduced to in this book is whenever an agent has extremely strong priors, like a rat who just really wants the cheese and doesn't even really care. It's not very risk averse, so it doesn't really care if it ends up choosing the wrong option and getting a small shock or something. It'll run right to the cheese. Those are all parameter settings that are determining that. And those are the parameters settings that we're trying to recover in the model inversion process. And that's why at step 5, we get this like reverse view of that same equation. Instead of having a sequence of actions given a parameter, now we're trying to find what is that parameter given the actual actions that we observed. That kind of tracks.
I'm sorry, Andrew.
Yeah.
Basic question. Could you please tell those values? What is it? P mu tilde? That's the policy. What is theta? What is O and what is M?
Yes, for sure. Theta are your model parameters. It's sort of like a collection of all these different parameters that might be involved in the model, right? So a lot of notation in other areas in active inference and elsewhere, it's like normally they would kind of put that in bold just to denote like, oh, this is a collection of different things. It's not just like a single value, right? So that might have been helpful if they used that. But yeah, so the theta are just these parameters that we're trying to recover about the model. M is just a symbol that throughout the book, sometimes you see an M being included in an equation. Sometimes you don't. But more often than not, it's implicit that M is almost always there. M just denotes this is a model. Like there's a model in here. And so it has its own parameters. It exists just point blank, like there's a model involved here. And so we have to say like, technically all of these parameters are conditioned on the fact that we have a model specified maybe in a certain way. For example, the M might also carry along the idea that, oh yeah, this is specifically a model in the form of a POMDP versus a different kind of model. So it's kind of there in part just as a reminder, and that's why it's often left out because it's already implicit that it's always there. And then finally, the tilde O, that is our sequence of observations. And so with a rat, like in a T-maze, just as we had, oh, the rat, like action 1, the tilde U, it took the hint, then after that it went for the reward. We know that those are recorded actions that the rat took. We also know the observations. That is, oh, the rat, whenever it took the action of going to the hint, we know that it observed the hint. so we can track that. Action number 2, it went for the reward and it successfully got it. It got the cheese. The observation in that case at time step 2 is that the rat observed the reward. So just as we have a sequence of actions, we also have an associated sequence of observations. And those are kind of those are the 2 things that we collect in empirical data, by which we now have like hopefully enough components to try and do this model inversion and extract those parameters that we cannot directly observe. Is that helpful?
Sure. Can I just clarify what I understood?
Yeah, absolutely.
Okay, sure. So what you're saying is, so okay, M is the model which we can think of like a configuration setting initially, which we pass on to the entire system, right? Like because every model can have a different configuration setting. Maybe that might serve what I'm saying. Your O tilde, right? What is it? O bar? O bar is like your
It's a tilde.
set
Yeah,
of observations,
squiggly
right?
bar. Yeah.
And then this O bar is like, it can be more than one observation, right? It can be like a sequence of observations, but we don't explicitly state what is the length of what is the like the slot of the sequence, right?
So we do technically know that, like in a
Okay, how?
a T-Maze example again.
Like based on your
Yeah, we have a certain number of time steps. So it's like, because that's what the POMDP is about. It's about discrete time steps. So it's like time step 1, the rat starts in the center. Like it's done nothing. There are no new observations necessarily, or maybe we say it didn't observe anything. It's just time step 1, there it is. Time step 2, it then goes to get the hint. It observes the hint. So now at time step 2, we were able to record, here's the action it took. And here is the observation it had. It observed the hint. Then time step 3, it decides to move to the left arm of the maze. And so we know that its action it took, the U, is that it moved left, and then it observed a reward. And so time step 3's O is it observed a reward. So you can imagine that as like 2 vectors almost of like, here's time step 1, here's time step 2, here's time step 3, here's the vector of actions it took from time step 1, 2, 3. Here are the observations it had at time steps 1, 2, 3. Right.
The 3 is a typical over here.
So, yeah, and in this case, it's been done in different ways for the T-Maze example. For example, and it's really useful because you can do things like try and study the so-called explore-exploit trade-off. So imagine you allow for 4 time steps. It's where the rat starts, and then it can choose to take the hint or not, and then it can go to the reward. Well, if you have 4 time steps, if the rat skips the hint and goes straight to the reward, well, now that you have that additional time step, the rat can spend more time with the reward. And so it's like, if you think about it in terms of it like maximizing its utility or reward, it's like, oh, it gets to spend a whole extra time step with that cheese. Like that's, great. It skipped the explore behavior, went straight to the exploit behavior to get as much cheese as it could. But then you can use that to try and study like, oh, this is a very like risk-taking rat, right? So it chose to do that versus other rats who might be more conservative and like go for the risk, go for the hint first, even though they're giving up that additional time step that they could spend spending more time with the reward. And then finally, you could also have very risk-averse rats who like, maybe they got shocked a couple times and they have preferences to really not get shocked. That those negative consequences in terms of its preference, highly outweigh its preference for the reward, in which case you might have a rat who just stays in the center the entire time, or it might go to the hint as a exploratory behavior to gather more info. It might go to the hint and not even trust it, depending on how you set up the situation, and it might stay at the hint and never go for the reward. It just really wants to know. It's so it's as if it's so talk about this in a sensitive way because it's a real animal, but like maybe it's so scared that it just keeps attempting to gather more info and never goes for the exploit behavior. So hopefully that's maybe a kind of an illustration of like, you know, we can choose the number of time steps whenever it comes to discrete time models like this. And so we can easily just index like time step 1, time step 2, etc. So was that helpful at all, Prakash? I might have been over descriptive with the T-maze example. There are plenty of other examples.
Sorry, actually, my internet got blocked out also. I had to reconnect. But actually, I think I get the picture. I like this that model example.
Cool. Yeah, I think it's a worthwhile one just because this chapter spends time on it, and that's kind of that figure 9.2. It's like, here's the series of steps you would take if you were doing the T-maze example. So it's like for anything that still seems ambiguous or uncertain, hopefully I'm giving enough info that you would come back to the chapter and see like, oh, okay, like I get it now with the T-maze example. Francis, you had a question?
Yeah. So that's really interesting and really helpful. Thank you. This may be a kind of blindingly obvious question. Is the focus of this book, or indeed of the active inference program in the general sense, more about understanding active inference as it exists, rather than, say, developing active inference as a generic AI technology to solve issues where we're not necessarily the generative model is not necessarily active inference related?
Yeah, I think that's a really interesting question. And it might be somewhere between, an answer to that might be somewhere between more objective versus highly opinionated. But I'll give my answer, which is, as far as I'm aware and looking at where you know, active inference can be applied to just kind of a ton of an immense amount of phenomena. Like here we're given chapter 9, applying active inference to empirical, where it can be applied to empirical data that we're collecting. And so we're looking at like actual agents. Active inference has many of its foundations in, you know, the work of Karl, Friston, and others who are coming from a neurobiological background. And so there has been kind of a big push initially to use this for those fields, and so computational psychiatry and so on. And we get a variety of examples of how that's been done in this textbook itself, in this chapter, like table 9.1. They provide an entire annotated like big bibliography of all these different works on delusions and pharmacotherapy interventions and so on. But that said, you could build models that like are entirely in silico, that don't have to do with analyzing, you know, animals or human beings. Like Thursday mornings, we were using ActInf, which is a package developed in Julia to try and build in silico experiments. And so what I'm saying with that is you could use these tools to build AI or otherwise different kinds of behavioral systems that you could, try and employ in the physical world. Like you could build a robot that has its own sensory modalities. It can see, visually what's going on, and then try and infer what kind of actions it should take and realize its preference. And of course, like if we build a robot, unless you're trying to actually emulate a human being or a rat, but probably not. You're probably building it to add to our reality and provide some kind of new function in society or otherwise, right? In that case, no, it would be more about like we're starting with simulating something on a computer that maybe one day can be realized in the form of like a physical machine. So yeah, it's kind of like these two worlds, right? It's like we can build active inference models to try and better understand the world around us, or we can build models that we can then actually employ, in the form of AI in society for whatever your use case is. And so you'll see a lot more literature that's been published, including since the textbook, that lends itself more to the latter approach that I described. But again, of course, this textbook is co-written with Friston and other folks with a neurobiological background. So I think if you really want to rely just on this textbook, you probably will get much more of the flavor, the kind of, psychological, psychiatric, biological flavoring of active inference. I hope that was a helpful kind of opinion that I shared there.
Yep. Thanks. I think that was very helped clarify what I was feeling my way towards. Thanks.
Sure, absolutely. Yeah, Prakash, good question.
Hey, hi, Andrew. I was since you mentioned about this Julia thing, right? And I was planning to join, but I've not been joining because I think I will start joining maybe the week after next, after I complete a few things. But I have a question. So I have never used Julia before, but I'm seeing that it's quite powerful and it's very fast, right? That's the most. It's like it's why people are using it. But I'm also wondering, since does it have integrations with, suppose, say, to tools like Neo4j, and has anybody worked on that? Like I was just seeing that they have a driver called bolt.jl, which does this. I don't know. I don't want to explore so much; it'd be crazy. But what I was thinking is, if we have like okay, well, let me make the question a little bit more simpler. Have you guys worked on any kind of when you is it entirely within the Julia platform, or do you also do some kind of integrations? So suppose
Sure.
because like in Python, if I use Python, for example, like, and I want to use other platforms also, the integrations are like much more like there are like good libraries which will help us, but over here it will require a little bit more level of.
Like we've not jumped into this knowing, for example, Julia and inside and out or anything. Actually, a PhD student who's working directly with the people who developed ActInf. So we do have like a little bit of support from someone who's been directly involved in building out the package and resources. But the majority of us have not even coded in Julia before. So it's primarily like many of us just kind of learning this together, and we're going through another nice thing. ActInf has their website where they've provided a series of like different coding examples for like different use cases. We did one that follows a Roomba, like a small machine that cleans your home, and trying to model like an inference process so that it can derive like a likelihood of like, oh, if I'm on top of tiles, I must be in the bathroom. If I'm seeing a hardwood floor, I must be in the living room. And so we just get these like nice like sort of real world use cases where we get to follow along and figure out how the code is functioning there. And more specifically, getting back to your question though, on integration, I'm still learning that myself, so I can't give a terribly holistic answer. But what I can say is that anytime we've run through any of these examples, for the most part, we're really just using like an updated baseline, Julia, like install that on your machine, pull it up. We use a nice visual editor called VS Code, if you may or may not already be familiar with that. And then in terms of just like bringing in the packages we're using, for the most part, it's just ActInf. It's not a ton of other, well, okay, to be fair, that has its own dependencies as well. But yeah, ActInf aims to be a kind of holistic, like this is the one package you have to pull in, and then maybe you pull in like an additional like nice like plotting package so you can like visualize the results of the inference process or otherwise that come out of ActInf. But yeah, I think ActInf aims to be a rather standalone asterisk package for yeah, building active inference models, both discrete time like POMDPs, or even just not even going that far in MDP, depends on your use case, as well as continuous models. And yeah, it's quite strong. And as far as previous approaches to active inference, like software wise, we have MATLAB, which has been more geared toward around building discrete time models, and Python, where the strongest like pre-established package for that being PYMDP, developed by Connor Hines and others. That's almost entirely like exclusive to discrete time steps. So Julia, yeah, something about the combination of computational efficiency with like, oh, there are developers who are creating these new kind of holistic packages for just trying to develop everything in one go in a single script. That's able to handle continuous processes much better and kind of more holistically as well. So I don't know. That was a lot, but I hope that was helpful in some way.
Just a follow-up question on Julia. Like what you're doing, are you like trying to say create some functions which will say do a thing like say minimize surprise or say calculate variational free energy for you guys? Like just create a function which will do that? Are we thinking on those lines also?
Yeah, presumably you could define your own. I mean, what's really interesting to me about Julia versus like Python is that you can actually like type in a theta and other symbols into the code itself as having to write it out. And so what I mean by bringing that up is that like you could certainly write your own sort of objective functions to energy minimization. What's nice is that ActInf, like some of its coding examples, very specifically relate to active inference. Like it is explicit, like it's an active model of building. And so there are functions like they have this infer parentheses function where you plug in, here's your model that you've just built, here's your data, simulate the behavior, and then they have a single argument for free energy, true or false. If you set it to true, it will minimize free energy. So it's kind of like all in-house, like out of the box, like if you want to do free energy minimization. There's on their website, they also have documentation for like is how they like within that function is the free that's being minimized, because at this point we have a few different kinds of free energy and formulations. Like in this textbook, for example, we're already introduced to the difference between variational free energy and expected free energy. And since then, there's been more research into other forms of free energy that are highly relatable, but nonetheless, like, for example, trying to combine, like, how do we put together variational free energy and expected free energy into maybe an even more concise single formulation, and with things like generalized energy. Another one be able to pronounce correctly, but I think it's Bertha energy or Beth energy, free energy, and that's highly used in this ActInf package. So yeah, summing it back up, there are ready to go, like out of the box free energy objective functions in the package, but you could define them yourself as well if you so chose. And Daniel's making a great point with the nodes. Another benefit of the ActInf approach, because I would say it's not just a package, but there's a lot of documentation on how it's its own approach. It is highly relatable to the textbook we're going through, and nonetheless it attempts to make some kind of advances on how to do active inference. So we end up with these things called constrained Forney factor graphs. We already see all of these different factor graphs in the textbook we're going through here. You know, the way the POMDP looks with like its nodes and its edges, and here's to visualize how it works. ActInf is doing the same thing, but it's attempting to make each node kind of self-contained almost, such that you just account for its connections with other nodes, and it will locally minimize its own free energy. In that case, like, rather than looking at a totality of the system minimizing some broader free energy, now you can look at it as, oh, each node in this graph is minimizing its own free energy based on its local connections only.
What's it called? Sorry,
This allows.
what is it called? What are you saying?
All right.
Just rename it, please. What you said, what is it called? What's the name?
Yes, the constrained Forney factor graph.
Oh, okay.
Yeah, and Daniel's typed it for the CFFG. Yeah, for sure. And then you'll see, like, what's nice, another thing is that in each of the examples, like, so if you go to the ActInf website, which you know, we've put links to that elsewhere in the coda, but a simple Google search of ActInf will take you right there as well. Each of the examples will cite a related paper. So like here's our code example. We've kept it really concise for you, but if you need more information on the simulation we're doing, the components, what the CFFG looks like for this, you can just go to the reference paper that relates to it. So we're part of the pull here for doing this project is that we are also giving feedback on the documentation for the package, since we have this kind of direct connection with the developers themselves. But so we've really been kind of scrutinizing the documentation a bit. Check out CFFG, because the whole idea is that you could go far beyond the kind of POMDPs we're seeing here in the textbook. You know, we end with a kind of a standard recipe for building those, but a CFFG, because each of the nodes is minimizing free energy locally, you could end up building, in principle, whatever kind of model you want. You could make it highly complex. All you have to do is specify here are the nodes connects, and you know, it uses message passing algorithms underneath to transfer all the messages between them. But yeah, you could make like any kind of arbitrary model basically, and like derive like free energy minimization for each of those nodes, and then you could potentially sum those up and look at like how the overall system is doing and such things like that. But yeah, in the interest of time, yeah, I would just recommend looking more into the ActInf package, and it sounds like something that might interest you. And then also we are posting in the coda like our notes and what's coming up in the next meeting.
The other option, the using active inference as a direct, the startups using active inference as a direct AI approach, rather than just using active inference, rather than using active inference to simply understand systems which understand.
Yeah, no, absolutely. I think the two kind of approaches go together too, right? Because so much of this is based upon neuroscience research towards, you can almost think of it as one of them is aiding the other. If we can learn how biological organisms learn, for example, that gives ideas of how to formulate a model that itself can learn, and then moving from that to building like a pure AI that's just using many of those principles we've derived for generating its own behavior, despite the fact that it itself is not a rat or a human being or some such thing. But yeah, please absolutely feel free to add to the code as you like, questions or notes or thoughts. So, thanks for that. So I think we've about
Thank you,
exhausted
Andrew.
Sure.
I'll stop recording.